this class we introduce the dual of a linear programming problem. We consider the maximization problem that we have seen before, and then we try to understand what is the dual and how a dual is formed from a given linear programming problem. So, let us look at the same linear programming problem that we have been solving and try to get an upper estimate of the objective function without solving it. So, let me explain this with the example. We look at this problem, which is to maximize 10x1 plus 9x2 subject to 3x1 plus 3x2 less than or equal to 21, 4x1 plus 3x2 less than or equal to 24, x1 and x2 greater than or equal to 0. Now, at the moment let us assume that we have not solved this problem, or we right now do not have a way to solve this problem, but we are interested in finding out what would be the upper estimate of the objective function without actually solving it. Now, we try and do the following things, and let me explain each of these one after another. Now, let us take the first constraint, 3x1 plus 3x2 is less than or equal to 21. Now, let us multiply the first constraint by 10. So, we multiply the first constraint by 10. So, if we multiply the first constraint by 10, we will get 30x1 plus 30x2, we will get 30x1 plus 30x2 will be less than or equal to 210. Now, this tells us something. What does this tell us? This tells us we also should have x1 x2 greater than or equal to 0. So, when x1 x2 is greater than or equal to 0, 30x1 plus 30x2 will be greater than or equal to 10x1 plus 9x2, because x1 and x2 are greater than or equal to 0. Now, the first constraint multiplied by 10 says that 30x1 plus 30x2 has to be less than or equal to 210. Therefore, 10x1 plus 9x2, which itself is less than or equal to 30x1 plus 30x2, will have to be less than or equal to 210. Therefore, we can say without solving that the value of the objective function at the optimum cannot exceed 210. This looks like a simple result. For example, if somebody says the optimum solution to this problem has an objective function value of 300, then based on this result we could say no, we cannot have the objective function value of the optimum more than 210. So, we understand up to that. So, we have now got an upper estimate of the objective function without actually solving it by using these constraints. So, at the moment this 210 is an upper estimate of the objective function value. Now, let us do this. Now, instead of multiplying the first constraint by 10, let us multiply the first constraint by 4 instead of multiplying the first constraint by 10, we multiply the first constraint by 4. So, the first constraint is multiplied by 4. So, if we multiply the first constraint by 4, we will get 12x1, because 3x1 plus 3x2 less than or equal to 21, when we multiply by 4 will give us 12x1 plus 12x2 less than or equal to 84. Now, we again learn something from this. Now, what do we learn? As long as x1 x2 is greater than or equal to 0, 10x1 plus 9x2 will be less than or equal to 12x1 plus 12x2, because this coefficient 12 is greater than or equal to 10 and this coefficient 12 is greater than or equal to 9. Therefore, 12x1 plus 12x2 will be greater than or equal to 10x1 plus 9x2. Now, if 12x1 plus 12x2 itself should be less than or equal to 84, then 10x1 plus 9x2 should be surely less than or equal to 84, and therefore we can now say confidently that the value of the objective function at the optimum will not be greater than 84, and 84 is now an upper estimate of the value of the objective function at the optimum. Now, so far what have we done? Based on multiplying the first constraint by 10, we said the upper estimate is 210. Now, based on multiplying the first constraint by 4, we have said that the upper estimate is 84. Now, between the upper estimates of 210 and 84, 84 is more meaningful because we can now say that the value of the objective function cannot exceed 84, and that is a more meaningful expression rather than saying it cannot exceed 210. So, what we have to do is, when we try and get an upper estimate, the smaller the upper estimate is, the more meaningful the upper estimate is. And then we have also now understood that if we multiply this equation or the constraint by a constant such that we are able to get the after multiplication, if we are able to get something such that the coefficients are related, then we can get the upper estimate. Let us continue this by doing something with the second constraint. Now, let us multiply the second constraint by 3. So, we multiply the second constraint by 3 to get 12x1 plus 9x2 is less than or equal to 72. Now, again going back, so long as x1 and x2 are greater than or equal to 0, 10x1 plus 9x2 will be less than or equal to 12x1 plus 9x2. And since 12x1 plus 9x2 itself should be less than or equal to 72, 10x1 plus 9x2 has to be less than or equal to 72, and 72 is now an upper estimate to the value of the objective function. Now, we have tried to calculate the upper estimate in 3 ways. And we got 210, we got 84, we got 72. Now, 72 is more meaningful than 84 and 210 because we are able to get a lower value of the upper estimate. So, 72 is meaningful, and we can now say that the value of the objective function at the optimum cannot exceed 72 without solving this problem. So, if somebody comes and says the value is 75, you can say that it cannot be so because our upper estimate is 72. Now, how did we get this upper estimate? We got these upper estimates by simply taking a constraint, and by multiplying the constraint with a positive, in this case a positive number, because if we multiply this with a negative number, the inequality sign will change. So far we have multiplied it with a positive number, or we may generalize it and say by a non-negative number, by a positive number, and by doing so after multiplication, if the coefficients after multiplication are individually greater than or equal to that of the objective function, then we could say the right hand side obtained after the multiplication is an upper estimate. In this case we multiplied by 10, the right hand side happened to be 210, the individual coefficients were greater than or equal to 10 and 9. Similarly, when we multiplied by 4, the right hand side came to 84, the individual coefficients 12 and 12 were greater than or equal to 10 and 9, and we got this. Similarly, for the third, using the second constraint, the third time when we did this, we multiplied by 3 to get 12 and 9, which were greater than or equal to 10 and 9, and therefore the upper estimate happened to be 72. So, we can now generalize and say that we can take any one of the constraints and multiply this constraint by a positive number, so that the sign of the inequality does not change. And by doing so, after multiplication, if the coefficients are greater than or equal to those of the objective function taken for every variable one at a time, then after multiplication of the constraint, whatever is the right hand side value is the upper estimate. Now let us do one more thing. Now instead of taking one constraint at a time, can we do the same thing with multiple constraints? Now in this example there are only two constraints, therefore we take both of them. If the problem had a larger number, we could take a subset. So if we take multiple constraints, we take two of them, multiply the first constraint by 3 and multiply the second constraint by 1, or simply add the second constraint. So when we multiply the first constraint by 3, we get 3 into 3. So what we do is, this is multiplied by 3 and this is multiplied by 1, which is the same as adding it. We get 3 into 3 9, 9 plus 4 13 as the coefficient for x1. Now 3 into 3 9 plus 3 12 as the coefficient for x2. Now this 13 and 12 are greater than or equal to this 10 and 9 respectively. Therefore the value 87, which was got by multiplying the first constraint by 3, 21 into 3 63 plus 24 into 1 gives us 87. Now 87 is an upper estimate of the objective function value. If it so happens that by now we have a slightly better estimate of 72, therefore one could go back and say, at the moment this 87 has not added too much value because 72 is a better estimate. But the idea is important. Rather than taking one constraint at a time, can I take multiple constraints at a time, multiply each of these constraints by a positive or a non-negative number, so that the sign of the inequality does not change, and then add, and after doing this multiplication and addition, if I will get a single constraint. For example, when we multiplied this by 3 and the second constraint by 1, we got 13x1 plus 12x2 less than or equal to 87. And after all this, if the individual coefficients are greater than that of the objective function, then the right hand side of the new constraint will be the upper estimate of the objective function value. So when we multiply, and we have to now suitably find out these numbers 3 and 1, 4 and 2, whatever it be, such that these individual coefficients will be greater than or equal to the corresponding individual coefficients. So we have learnt one thing now instead of two. We started by taking one constraint at a time, but then now we have said that if we take multiple constraints and we can do the same thing, we can also show that taking one constraint at a time is like taking more than one and giving a weight of 0 to some other constraint. So if we can take any subset of constraints, multiply them by a non-negative, in this case positive number, and add them, so that the inequality sign is not affected. And after doing so, we will get a single constraint, and if that constraint is such that the left hand side coefficients are greater than or equal to that of the objective function coefficients variable by variable, then the right hand side is an upper estimate of the objective function value. So now using these 4, we have come to a thing that 72 looks the best upper estimate, but more importantly the idea behind the fourth one, where I can multiply the constraints by a certain non-negative number and add them, is something that is important, and we carry that further. So what do we do next? Now we go back and say that we have written the same problem again for reference. Now I go back and say, instead of multiplying these constraints by some known numbers, we did 3 and 1. Now I am going to say that if I multiply the first constraint by A, if I multiply the first constraint by A, I multiply the first constraint by A, I multiply the second constraint by B. At the moment I do not know B, A and B, but if I multiply them by A and B, and I have to make sure that A and B are non-negative, otherwise if I multiply this with a negative number, I will get minus 3x1 minus 3x2 will be less than or equal to minus 21, minus 63, or if I multiply with minus 1, I will get minus 3x1 minus 3x2 is less than or equal to minus 21, which will become 3x1 plus 3x2 greater than or equal to 21. So I should not multiply at the moment, I should not multiply with a negative number. So A and B have to be greater than or equal to 0. So when I multiply the first constraint by A and I multiply the second constraint by B, the new constraint for x1 will have 3A plus 4B. Now A and B have to be such that 3A plus 4B is greater than or equal to 10. Such that now A and B have to be such that 3A plus 4B is greater than or equal to 10, and they also have to be such that 3A plus 3B greater than or equal to 9. So 3A plus 3B is greater than or equal to 9. If I am able to get A and B that satisfy these two conditions after multiplication, then 21A plus 24B is an upper estimate of the objective function value. Now that is the generalization that we have made based on what we have seen earlier. Now we go back and generalize it further. Now if we want to minimize that upper estimate, then what are we trying to do? If we want to keep that upper estimate as small as possible, now we have to find A and B such that 3A plus 4B is greater than or equal to 10, 3A plus 3B is greater than or equal to 9, and 21A plus 24B is as small as possible. So now A and B have to be found such that we minimize 21A plus 24B subject to 3A plus 4B is greater than or equal to 10 and 3A plus 3B is greater than or equal to 9, A and B greater than or equal to 0. Now we realize that in the process what we have done is we have formulated another linear programming problem, which is this. Now we have formulated another linear programming problem which is given by this, where now A and B are variables. Now to give a formal structure to such a linear programming problem, we replace A and B by new variables called y1 and y2, and if we do so, the new problem becomes minimize 21. After doing this, we will get minimize 21y1 plus 24y2 subject to 3y1. Now A is replaced by y1 and B is replaced by y2. Now 3y1 plus 4y2 is greater than or equal to 10, 3y1 plus 3y2 is greater than or equal to 9, y1 y2 greater than or equal to 0. So starting from the given problem which is here, we tried to get an upper estimate of the objective function value, and we ended up creating another linear programming problem which is given here. Now the original problem that we had is called the primal, which is given by P, and the new problem is called the dual. It's called the dual. called the dual. Now for every linear programming problem which is called as primal, there is another linear programming problem which is called the dual. In the next class we will see how we can write the dual directly from the primal without going through the process of evaluating the upper estimate.